good morning and good afternoon because we are facing the time of difference between China and Japan. My name is Han. I'm working at Riken, Cluster for Pioneering Research CPR, and also working at Ride Company, Japan. Today I would like to talk about high injection current density via aluminum graded undoped-AlGaN cladding layer, and also aluminum graded p-AlGaN whole source layer. Here is the outline of my presentation. Wide range of application of UV laser diode will be discussed. As a background, crystal quality and the internal quantum efficiency of the AlGaN based quantum structure will be discussed, and some stimulated lasing by optical pumping will also be discussed. Some challenges, for instance, highly conductive polarized cladding layer and aluminum graded magnesium doped p-AlGaN whole source layer for electric pumping will discuss. Some structural optimization of UVC laser will be discussed too, and then ultimately we will demonstrate to the electrically pumped UVB laser diode. And we will also present some investigation of net modal gain for UVC using SiLENSe, and then summarize my talk. UV laser diode has a lot of application, from sterilization and also to high density recording laser and rapid decomposition of the pollutants, and also for medical application for LASIK, for eyes treatment, and also for the COVID application too. And by using the AlGaN and aluminum nitride materials, high efficiency laser diode is expected. A group 3 nitride semiconductor has a wide band gap. P-type and N-type is possible, and this material is hard in nature and also environmentally safe to respect Minamata Convention of 2020, and also to respect the 17 Sustainable Goals of United Nations. Problem and challenges: the epitaxial growth of good quality on an aluminum nitride template is quite challenging. Issue of hole injection toward the quantum wells for lasing is also very challenging. Why we need AlGaN based UVB laser diodes? Typical laser processing uses infrared light. However, due to the high energy absorptions rates by metallic materials, demand for short wavelength deep UV laser sources are increasing. However, currently deep UV or UVB laser light sources are obtained through wavelength conversion by using complicated nature of the configuration of laser sources, which creates some issue with environment, large in size, you can estimate, and it consumes a lot of energy. So we need a smart, lightweight, environmentally safe UV laser sources for industrial and medical applications. Here I would present the short history of the short wavelength 271 nanometer UV laser diode, which was demonstrated by Professor Amano group at Nagoya University. They grow the device structure on the aluminum nitride single crystal substrate, which is quite expensive. Also, Professor Iwaya group at Meiju University, Nagoya, also demonstrated 2 UVB laser diode at emission wavelength of 298 nanometers. But this device was grown on sapphire. But they first introduced the sputter aluminum nitride, and then regrown of aluminum nitride, and then next they grow 9 micrometer, quite thick, an AlGaN cladding layer, and these approaches seems to be expensive. Here at Riken we choose a different route of ammonia pulse flow multilayers growth to achieve our target of highly efficient LED and laser diode on aluminum nitride template. We also need high internal quantum efficiency. So in ammonia pulse flow multilayer growth, we use aluminum source and also pulsed ammonia source shown here, and we can grow very good crystal quality of aluminum nitride template on sapphire, where the threading dislocation density 3 × 10⁸ per centimeter squares were successfully obtained. The next step is to grow AlGaN based quantum well structure, but AlGaN and aluminum nitride has the lattice mismatch of 2% around, depends on the emission wavelength of the UVB laser. So we used low pressure MOP system at Riken to grow quantum well structure and laser diode structure too. First we grow the optically pump laser diode structure, which we grow on the 4 micrometer thick aluminum nitride template. Very thin layer of 1.8 micron of AlGaN cladding layer were introduced, which is contrary to the major university where they use 9 micrometers. And then here we grow the quantum well structure, and then the undoped-AlGaN OCL, and here is the undoped OCL. So the laser diode structure was like this. Ultimately, the threshold excitation power density was improved. A record low threshold excitation power density of 26 kilowatt per centimeter square at room temperature was achieved, and also lasing spectra at room temperature was also observed in optically pumped laser diodes. This work is published here, and some discussion is also given in this paper. We have a very, of course, we got very high EQ in the quantum well, and we have no problem with the N side of the AlGaN, but the problem is the P side, because the low hole injection is quite challenging, as I mentioned in my introduction part. These grown structures to make the ridge structure of the here is the SEM image of the process UVB LED structure. You can see the end of the P electrode here. This is SiO2 was covered this part, and here's the mirror structure. So this on the ridge, the partial SiO2 peeling was a problem, but later we resolved this problem. And we processed the laser structure. Structure was around 300. This was relatively more smaller wavelength of 285, and again we could get very high current density of 100 kiloamps per centimeter square. In this case, we used the region length of the laser diode about 4 micron and 400 micron. Here the pulse width was 50 nanosecond. So in this case, we have the problem with the waveguide layer thickness. I will just briefly, because we could not get lasing, but we got some abnormal oscillation that we will report later. So anyway, this is the device structure, which experimental device structure is given in this table. So the length of the N waveguide and P waveguide was not optimized. So the light confinement factor of 1.77% was achieved for this. So we also checked the P waveguide side with magnesium and without magnesium. That's what happens. So this is the overall scenario. What we tried to see the gain. So here is the refractive index data, and here is the absorption spectra. So with magnesium dop of the P waveguide side, we could get the optical loss was 22.7 centimeter inverse. So it was very high. So what we did, we changed. First we changed the waveguide. We rearrange the waveguide, and also we remove the magnesium doping from the P waveguide, and we could reduce the optical loss from 22 to 8.7. So this structure is very nice, and the optical confinement factor was 4.6%, was achieved through simulation. So in the near future, we would like to use these new improved structure for the laser diode, and probably we can get the lasing. So we are just behind one step lasing. So here is the current density dependence of the net gain. So here's the net gain and current density. So the original, which I showed, that the sample was here, but later the simulated one without magnesium doped P waveguide layer shows very high net gain. So we will use in the near future this configuration. And also we found in experimental laser diode, we found one problem, that the quantum well thickness was 4 nanometer, which was not good. And when we use a 4 nanometer, so we could get very high net gain in that case. And also in that case the injection efficiency was also enhanced by using a thicker quantum well in the laser diode. Let me summarize my work. A polarization induced aluminum graded AlGaN cladding layer, which is undoped, was employed to achieve improved conductivity as well as hole injection toward quantum well. The injection current density were drastically improved from 5 kiloamps per centimeter square to 100 kiloamps per centimeter square at 285 nanometer emission wavelength by using the ridge width of 4 micrometer and length 400 micrometer under pulse operation. By making the P waveguide layer non-doped and increasing the quantum well thickness from 2 nanometer to 4 nanometer, the internal loss was greatly reduced from 22.7 to 8.7 centimeter inverse in the revised LED design. This is the theoretical result. The maximum gain was confirmed in sample 3, which is of course is the theoretical model. We will grow epitaxial laser diode structure based on the improved theoretical design to get the lasing in the near future. And at the end, we would say many thanks to the NATO Japan for their financial support, and also thank you all for your kind patience.